Hi everyone, welcome back to Dave's Math Channel. I'm host David Tear, and this is going to be my last of four videos in a series about infinity. Today I'm going to talk about an infinity of infinities. So in the last video, I explained why there's more real numbers than rational numbers. So we actually have two sizes of infinity. We have the what's called aleph null, which is the cardinality of the integers also equal to cardinality of the rational numbers. But then the last video I showed that the continuum, usually denoted by the letter C, is a bigger infinity. That's the size of the real numbers. Well, it turns out there's actually infinitely many cardinal numbers, not just those two. So anyway, let's get going with this. So I'm going to give you a brief review about cardinal numbers. So what do we mean by the cardinal number of a set? Well, the kind of simple definition is just the number of elements in the set. But that works for finite sets. So for instance, here's the two sets X and Y, both with exactly four elements. We say that the cardinal number of each set is four. But we could still determine that they have the same cardinal number even without having to count the number of elements of each set. And the way we do that is with this what's called a bijection or one-to-one correspondence. So what we do is we draw arrows from element of X to a unique element of Y, such that every element of X is paired up with exactly one element of Y. This is called a bijection in set theory. So as long as there exists a bijection between two sets, that means they have the same cardinal number. So in this case, the cardinal number is 4. But it doesn't just work for finite sets, it works for infinite sets as well. So here's an example of two infinite sets. As a matter of fact, these have countably infinite sets. Their cardinal number is aleph null. So here what we do is we have an x, notice, is the set of all positive integers, 1, 2, 3, up to infinity. And y is a set of all positive even integers, 2, 4, 6, etc., up to infinity. And I talked about this in previous videos. This is a bijection as well because we can map the element 1 of x to the element 2 of y, 2 to and x to 4 and y, 3 and x to 6 and y. And in general, we can map the element small x and big X to small 2x and big Y. In other words, every element of x is just matched up with its double in Y. So that proves that the set of all positive integers has the same cardinal number as a set of all positive even integers. This is a basis for one of the paradoxes in Hilbert's Hotel because you can still add the odd integers to y and then you get back x. So this kind of shows that y is bijectively equivalent to a subset of x, but they have the same cardinal number. But now, in the last video, I talked about how I explained Cantor's diagonal argument, how you could actually show that there's more real numbers than rational numbers or than integers. Well, here's another picture of that argument. I mean, in the last video, I wrote down the base 10 decimal expansions of a supposed list of all real numbers. You can do the same thing in base 2. So just imagine that these strings of zeros and ones you see on top are uh, are the binary expansions of numbers between 0 and 1, which all have repeating decimal. They don't show the decimal point here, but imagine there's a decimal point to the left of these strings of zeros and ones for each of these numbers. Well, then you can make a new number on your list. It's just the binary number beginning with a decimal point such that the first digit, which is 1 in this case, of S is different from the first digit of S1. There's only two choices for all these, so this gives us a unique choice for X, S. The second bit is 0 because the second bit of S2 is 1. Third bit is 1 because the third bit of S3 is 0, so on. This gives you a new real number that's not on your list. Or you don't even have to think about real numbers. You can imagine these are just infinite strings of zeros and ones. And this kind of argument, this is Cantor's diagonal argument, which I showed you last time. It shows you that there's more real numbers than integers or positive integers. But you can actually use this argument more generally for power sets. One thing I didn't point out here, so I guess I have to define a power set first. Well, a power set is just a set of all subsets of a given set. So here's a simple example. Suppose we have a set with just three elements, which we can call X, Y, and Z. Then the power set of S, so S is the set containing the elements X, Y, Z. The power set of S, which we usually write as P of S, is the set of all subsets of S. And you see that there's eight. There's exactly eight subsets of S, which is 2 cubed. And the subsets of S, they're shown in this diagram above. There's a name for that diagram. I forget what it's called, but it kind of looks like a cube in this case. So the thing at the bottom is just the empty set. And then, then the other elements, I guess the elements on the second level, you're going from bottom to top. The elements on the second level are just the singletons. This subset containing just the single element X, the subset containing just the element Y, and the subset containing the element Z. But then you go to the third level, and then you get all the subsets with exactly two elements, and there's exactly three of those as well. You have the subset X comma Y, subset X comma Z, and the subset Y comma Z. And then on top, you have the whole set. That's just X, or the set containing the elements X comma Y comma Z. So in general, I think it's not too hard to see that if you start with a set of with n elements, where n is just a positive integer or non-negative integer, you can start with the np set as well. Then your power set is going to be a set with exactly 2 to the n elements. And one thing you should notice is that 2 to the n is always strictly greater than n. For any non-negative integer n, that's true. I mean, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the cubed is 8, so on. The powers of 2 grow a lot faster than the positive integers, non-negative integers. So that shouldn't be too surprising. But what things get more interesting when you start thinking about power sets of infinite sets. You can do the same thing with infinite sets. And that's basically what we did when we did Cantor's diagonal argument. Let me just go back to the slide with Cantor's diagonal argument. So imagine your set you're starting with is just a set of all positive integers, 1, 2, 3, so on up to infinity. What's the power set? I mean, we can call that set n, blackboard n, capital N. So what is the power set P of blackboard n? Well, it's a set of all subsets of n. And I guess what they're showing here, is that what they're showing here? Yeah. So what is a set of all subsets of n? It's just the set. So I mean, just imagine you have a subset of n, a subset of the integers. Then just consider a particular integer, say the integer x, and then you can assign either a 0 or a 1 to x, depending on whether x lies in this particular subset. And that's kind of what they're doing here. So s sub 1 is a particular subset of the integers. As a matter of fact, it's the empty set because every element is 0 here. That means that no element of the positive integers belongs to this set. That's why we get all zeros. And then S2 is just the whole set of integers, positive integers. And then if for any positive integer you pick, you're going to get a 1 because that element does lie in this set. And then S3, I think you can kind of see patterns here. S3 is just a set of all the even integers, and that's why you get a 0 for all the odd integers, a 1 for all the even integers. And you can do this for any set you want. So any subset of the integers is going to give you a unique string of zeros and ones. And that's one way you can represent the power set of the integers with these strings. And you can apply Cantor's diagonal argument to this and show that you can get a subset of the integers that is not on this list. So in other words, the set of all power sets, the set of all subsets of the integers is uncountable. Even though the positive integers are countable, the power set of the positive integers is uncountable. We just proved it here using Cantor's diagonal argument. And as it turns out, you can apply Cantor's diagonal argument to any set. It doesn't have to be, it'll work for finite sets. It'll work for a countably infinite set, but it turns out it works for every set. And the way you do this, instead of if you're working with an arbitrary set, you can no longer write s sub 1, s sub 2, s sub 3. You have to use a function. And they kind of do that here. I don't really like this slide that much because the arguments are always positive integers. This is basically the same argument we saw before. But I wrote out the argument. Here's the general argument. So this is Cantor's general diagonal argument. I wrote it out myself. So let S, capital S, be any set you want. It could be finite, could be infinite, could be countably infinite, it could be the integers, it could be the real numbers that's not countably infinite. Just any set in the world. And then consider the power set, P of S. And now what we're going to prove using Cantor's general diagonal argument is that P of S, the power set of S, the set of all subsets of S, is strictly has a larger cardinal number. It's a bigger set than S. And the way we prove that is we show that there's no bijection. Remember, if sets have the same size, that means there's a bijection from one to the other. So if we can show that there's no bijection from S to P of S, then we've shown that they don't have the same cardinal number. But that means that P of S is either smaller than S or bigger than S. It's obviously not smaller because all the singletons, right? If you take the subset of all the singletons of S, that is bijective with S. So P of S has at least as many elements as S. That's pretty easy to see. So if there's no bijection, that'll prove that P of S is strictly greater than S. The cardinality of P of S is strictly greater than the cardinality of S. Well, here's how the argument goes. So this is an argument by contradiction. Let's assume that there is a bijection between all the subsets of S and S itself. That's what we're assuming to start with. And now we construct a subset, which we call capital D of capital S, which by definition consists of all the elements little s of capital S, such that f of S, f is our presumed bijection. So f is just a function from S to the power set. It's supposed to be a bijection. So we can say that f of S, that's going to be a subset of capital S, and we can just look at all the subsets of capital S that don't contain the argument little s. And we can define the subset D. This is kind of like the reason I called it D is we're basically using a generalization of Cantor's diagonal argument here. And now, if we assume that F is a bijection, that means that there has to have been some element little d of S, such that capital D is F of little d. But if we assume that, then we get a contradiction because then we can just substitute f of little d for capital D. And then we can see from the definition of capital D that f of d, f of little d cannot contain little d, or it contains little d if and only if it doesn't. That gives you a contradiction. So that is Cantor's diagonal argument. The one I showed you yesterday is a special case of that when we're dealing with the positive integers, but it worked for any set. So if you use Cantor's diagonal argument for any set S, no matter how big it is, then the upshot of it is that you get a contradiction. You get that f of little d contains itself if and only if it doesn't. So anyway, that proves that the power set of capital S, no matter what capital S is strictly greater than capital S. And what's interesting about this is we can start with the integers. I'm just gonna. I mean, I'm sort of jumping the gun here, but I'm just gonna. This is the last slide in my picture. So for the special case of the integers is this set indicated by letter box capital N. That's just a set, 1, 2, 3, etc., up to infinity. And if we apply Cantor's diagonal argument to the positive integers, then we've just shown that the set of subsets of the positive integers, which we showed was bijectively equivalent to the real numbers, just by considering binary digits, and we call that we call the cardinality the real number C, which stands for the continuum. Well, we've proven by Cantor's diagonal argument is that C is strictly greater than Aleph null, which is the cardinality of the positive integers. But like I said, this is we could prove this result using the special case of Cantor's diagonal argument applied to the positive integers. But since you can use it for any set you want, say capital S is any set, could be finite, could be infinite, could have any infinite cardinality, and let's call that cardinal number K. So then what we've proven is that the cardinality of the power set of S, which we usually call 2 to the K. I won't explain why we call it that, but it turns out that when S is any set with a cardinal number K, then the cardinal number of its power set is 2 to that power. I think I explained that for finite sets. It's also true for infinite sets. We can kind of define 2 to an infinite cardinal this way. But what Cantor's diagonal argument proves is that 2 to the k, whatever k is, 2 to the k is strictly larger than k for any cardinal number k, whether it's finite or infinite. And since you can raise any cardinal number to the power, you can raise 2 to that power for any cardinal number k. You can do this as many times as you want. So that actually proves that there's infinitely many sizes of infinity, because the smallest is Aleph null. 2 to the Aleph null is what we call C, and then 2 to the C is going to be strictly greater than C, and so on. We could keep giving names for these bigger and bigger cardinal numbers. As a matter of fact, I think this has been done. We use bet, which is the second Hebrew letter. I didn't do it here, but bet naught. There are set theorists who use this notation. Bet naught is the same as Aleph null, bet null. That's the cardinality of the positive integers. And then bet 1 we just defined to be 2 to the bet naught, bet 2 to be 2 to the bet 1, bet 3 2 to the bet 2, and so on up to infinity. And in general, bet omega plus 1 is 2 to the bet omega, where omega is an ordinal number. I'm just going to finish by talking about the continuum hypothesis and the generalized continuum hypothesis. These are assumptions you actually have to add to set theory. You can't prove them or disprove them. Their versions, I think it was, I don't remember who proved this, but it was proven in 1967, I believe, that there's versions of set theory in which the generalized continuum hypothesis is true, and then there's other versions in which it's false. Kind of a weird result. So it depends on what kind of assumptions you want to put in. Kind of like the parallel postulate and geometry. You get different kinds of geometries if you assume or don't assume the parallel postulate. Similar, you get different versions of set theory if you assume or don't assume the continuum hypothesis or the generalized continuum hypothesis. Anyway, the continuum hypothesis just says 2 to the Aleph null is Aleph 1. And what Aleph 1 is the next biggest cardinal number, next smallest cardinal number after Aleph null. So we can kind of order all the infinite cardinal numbers. Aleph null, by definition, is the smallest infinite cardinal. That's the cardinality of the integers. Aleph 1, if the continuum hypothesis is true, then Aleph 1 is equal to C. Aleph 1 is the cardinality of the real numbers. But that doesn't have to be true. And there are other versions of set theory in which it's false. And it's a little weird. I can't imagine any sizes of infinity that are between the size of the integers and the real numbers. But there are versions of set theory in which there are sets whose size is in between. And I think actually a lot of set theorists prefer having them. I don't know why. But then the generalized continuum hypothesis just says that if omega is any ordinal number, and maybe it's easier to think of omega as a finite number, it doesn't have to be finite, but say omega is 5. So what the generalized continuum hypothesis would say in this case is that 2 to the omega 5 is equal to omega 6. So in other words, the sixth smallest infinite cardinal number is just the one right after the fifth. I mean, that's obvious. But 2 to the power of the fifth smallest cardinal number is the sixth smallest cardinal number. There's nothing in between. And this holds for any ordinal number omega. And ordinal numbers can be infinite. Ordinal numbers are kind of weird. I'm not an expert on this stuff, but anyway, I've said pretty much everything I know about this. So basically, we've proven that there's infinitely many sizes of infinity, and that's true whether or not you assume the generalized continuum hypothesis or the continuum hypothesis. Anyway, that's my last talk on infinity. I hope you enjoyed it, and I'll see you next time.